AP Physics B, the 19th learning target, as we have the numbered, states that students should understand Newton's third law so that for a given system they can identify the force pairs and the objects on which they act and state the magnitude and direction of each force. Newton's third law is one that I'm sure you probably have heard before and probably could even recite. It starts out for every action, and then you probably know it ends, there's an equal and opposite reaction, but people get the wrong idea about this. They think of it as cause and effect. I think the action-reaction thing confuses people. So like if I call somebody a name, they might come and punch me in the face. That's something that happens, and then something that happens as a result of it. But that's not a Newton's third law action and reaction. Action-reaction with Newton's third law is talking about forces, and they're forces that happen at the same time. So, classic example of this is that when I push on the board pushes back on me, or when I push on the wall pushes back on me. Now these forces happen at the same time, so I push on the wall and immediately it starts pushing back on me. I know this because I don't fall through the wall. I also don't walk away and suddenly, the board is pushing on me after I've walked away. No, it happens at exactly the same time. Those forces, they're in opposite directions, so I push that way at the board, and the board pushes this way on me, and I know that it's pushing this way on me, because if I try and do the same thing with the board not there, there's nothing to keep me from moving this direction. In addition to happening simultaneously and in opposite direction, these two forces are equal in size or in magnitude. So if I push with just a little force toward the board, I can feel just a little force coming back. A lot of force toward the board, and I feel a lot of force coming back. And if I give it a really big force, slam my body into this, it's going to hurt me because it's a big force coming right back at me. These forces are simultaneous, they're in opposite directions, they're equal in magnitude, and last part, they act on two different objects. I'm interacting with the board, and I get one of these forces, and the board gets one of these forces. I push on the board, that's a force on the board. The board pushes back on me, that's a force on me. Newton's third law of pairs have to act on two different objects. So maybe a better way to understand Newton's third law than for every action there's an equal and opposite reaction is that forces are interactions between pairs, between two objects. And those forces also come in pairs, in twos, with one force acting on one object and a second force acting on the second object. Those two forces happen at the same time, they last the same length of time and the same duration. They're equal in size and they're opposite in direction. Now, one piece that we need to do with this then is start to identify force pairs for a given situation. So let's look at a nice simple one where we have two boxes stacked on top of each other. And we'll call this M1, and this one is M2. Now we've got lots of forces that could be involved here, especially if we, say, push one of these boxes or push both of these boxes. But even just for a simple case here, we can look at some force pairs that go along with the situation. Now let's say these are at rest on some surface, maybe a table. Oops, marker's dying. So they're at rest on a table. They're not being pushed. They're on the surface of the earth. There's gravity pulling them both downward. So let's identify some forces that act on each of these. So for mass 1, let's do a free body diagram. Like I said, there's gravity acting on this, so it's got weight downward, which has a magnitude equal to mass times gravity. Mass times the acceleration of gravity, 9.8 meters per second squared. It's also got a force upward that's keeping it from falling through mass 2. Now, in some situations, we might call that a normal force. It's perpendicular to the surface, or normal to the surface. It's upward. Here, though, I'm going to be a little more specific and call that the force that's acting on mass 1, so on 1, by mass 2. So F1 by 2. So that's the force on mass 1 done by mass 2. Mass 2 is pushing on force 1 here. Now if we looked at mass 2, we're going to have a fairly similar picture. We've got still weight downward. Weight is equal to mass, that's mass 2, so it's mass 1 times gravity, those vectors. This time we've got a force from, well, I guess the table there that keeps that mass from falling through the table. So I'll put that up here. Force, call that table on the box, T on B. And that's an upward force, and that must be exactly the same as the force that mass is applying to the table. We'll get to that step in just a minute. And then a third force, we've got this mass 1 that's pushing down on mass 2. Now that one we'll call the force from mass 1 on mass 2. Or from mass, sorry, change my notation here. Force on mass 2 by mass 1. Now, this should look familiar because it's the same as this, just flip-flopped. Now, the force on 2 by 1 and the force on 1 by 2, that's a Newton's third law pair. That's two forces from two different objects acting on each other. They happen in opposite directions. This one's downward, this one's upward, and they're equal in magnitude. So I could further state that the force on 1 by 2, the magnitude of that, is equal to the magnitude of the force on 2 by 1. They're just in opposite directions. Now these are not the only Newton's third law pairs in this situation. We've also got the table involved here, and we've got the Earth involved here. This isn't really a two-object system. It's at least a four-object system. So for each one of these weights, that's a force downward on those masses by the Earth. There's also a force upward on the Earth by those masses. So this weight, mass 1 times g, would be equal to the force upward on the Earth by mass 1. And this weight, m2 times g, would be equal to the force upward on the Earth by mass 2. We've also got the table involved here that's feeling a force downward in direct contact with m2. And that force downward on the table is exactly equal to the force upward on m2. That's the force from the table on the book. I should change that to m2, I guess. So this force has to be equal to the force downward on the table. Now that's true even if we have acceleration going on here. Now if, say, the table is just broken, then we're going to have this object moving downward. You might think, well, okay, the downward force must be bigger than the upward force, otherwise it wouldn't be falling downward. But remember, these two forces act on two different objects. So this downward force on the table stays the same, stays equal to the upward force from the table on mass 2. It just gets smaller if the table breaks, or becomes 0, I guess, at some point when that table is completely split open. Now, another interesting problem we could go into here is, what if we pulled one of these or pushed one of these on the table and we have friction involved here? Well, in that case, we have friction between, say, M1 and M2 that would act in one direction for one object and in the other direction for another. In these situations, it's useful to think about what happens if there's no friction and then compare it to the real situation. So let's say I put a hook or a handle on M2 and I start pulling it with a force this direction. Now if you think about this situation, if there's no friction, there's nothing between M1 and M2 to make M1 move this direction. So M2 gets pulled this way, M1 just falls off the other edge. So M2 moves over, M1 stays right where it is and pops down in M2's place. With friction, we know that M1 is probably going to move with M2. Unless I really jerk it, then, well, it'll still move this direction a little bit, but maybe not enough to stay on M2. From all these things, I can see that what friction does is it makes M1 move this way. So friction between these two must act this direction for M1. Now, I also know that this is going to be more difficult to move because M1 is stacked on top, and if I put something really heavy on there, think about trying to slide a paper across the table and there's a textbook on top of it, or something even bigger than a textbook, someone's standing on it. That's a lot tougher to do than just the piece of paper by itself. So I know that there must be a force this way on M2 from M1. Those two forces, again, are going to be equal in size and opposite in direction. So even though it's still just a frictional force, there's really two frictional forces, one on M1, one on M2. For M1 it goes this way, for M2 it goes this way. They're equal in size, opposite in direction. They act on two separate objects and they happen simultaneously. That's a Newton's third law pair of forces.